So I'm Tavs Jorgensen. My background is I trained as a potter, but I am an academic now. So I'm an associate professor at a research center called Center for Print Research in Bristol. And we've been working on a project about extrusion. So if you've all been to the brick factory here, they don't actually do extrusion. But extrusion is a very, very common and very efficient way of producing brick in the ceramic sector. So you see the extrusion process here on the left. A big machine that squeezes the clay through what's called a die, the profile that shapes the brick, and then millions and millions of bricks here on the right. So it's a really efficient and quick way of producing or mass producing bricks. But it's really worth highlighting. So as I said, I'm an academic. I work in a research center. The key thing about doing project is to get funding. So I just want to show you just a picture of what it takes to start a project. So whenever we start a project, and particularly this is the application for the extrusion, you write a bid to the research council. It takes probably about a month full time. It usually takes more than that, but kind of not full time. So it probably took 3 or 4 months to create a bid like this. But it's absolutely critical to get funding to do projects, and so with the extrusion project here also. And it's normally about 15 to 20% chance. So you would write 5 of these before you actually get successful. So it's a big part of what I do, but I think it's really important to highlight that the skill in terms of getting funding is kind of critical to move things on, and also in terms of earth bricks we're going to talk about here. So back to extrusion. There's 2 basic principles of extrusion. One with auger base, so it's a big screw that squeezes the clay through a die, or there's the piston ram extrusion, so essentially just like a syringe that pushes the clay through and out and shape. And it's kind of relevant that you know these 2 principles as we move on here. So in industry, the extruders look like this, and if you want to do research, it's very difficult to get access to a big auger extrusion. So that's with the big screw that pushes the clay out. So it's a continuous feed. So they run for weeks, months, years, decades, just kind of the same, and it's a loop, so you keep feeding in and it just keep pushing, so it doesn't retract. But if you want to do research, it's very, very difficult to get access because they're always in use, and it's a very expensive piece of kit. So you can't just, even with a lot of research money, one of these are hundreds of thousands, if not millions. So in order to do the research, we bought the biggest kind of extruder we could find that was not industrial. We had to import it from the States, and even though we specified the electricity, as soon as we plugged it in, it blew up. So we were really screwed in terms, so they didn't realize that 3-phase is not the same as 3-phase in the UK. So we were really screwed in terms of doing the research. And because we had to have an extruder to actually explore new ways of, new approaches with the extrusion process. That was really what all the research was about, is kind of this very established industrial process. How can you innovate with that process? It's been, the same thing's been done with extrusion as it has been for decades. That was really what the research was based on. So we had to build our own, and there's quite a lot of waste around universities. So something Unistrut, which some of you might be very familiar with, really useful kind of system of kind of metal framework. So it's like a big Meccano. We built the frame. And then, rather than the auger-based extrusion, which is much more difficult to engineer, we just built a very basic piston extruder. So we just bought some pipe off the internet, put some flanges on, and then we bought a hydraulic ram. Again, these are very accessible. You can get them, get a kit, for less than £1,000. Incredibly powerful. They're used in all sorts of things. You obviously see them in Digger, and to create a very basic ram extruder like this was actually really, really very affordable. So all the materials and the hydraulic system, less than £2,000. So we could get going for really very very low cost. And this is, as you see further on, the vision of this project is really to create a system that other people can use, that other people can experiment with, that is affordable. So, the process of extrusion can be explored by others. It's really to pass on that kind of knowledge. Then onto the dyes. So the dyes are the profile that actually shapes what you are pushing through the extruder. In industry, they're either really, really heavily engineered, as you see there up on the top left corner, and they're heavily engineered just to withstand the wear. Because if you're producing millions and millions of bricks, then you have to lubricate it, and you kind of make sure that the clay flows, and you want to keep on going for just with the same standard. So they're very highly engineered, but that means you stay with one shape. You just you produce the same brick over and over again because it's expensive to change. If you are changing, that they're really, really basic. They're generally just kind of sheet of metal with a plasma cut profile. So it's either really engineered or really basic. They've completely missed out what has been happening over the last couple of decades in terms of digital fabrication. 3D printing has become so incredibly affordable, but it's really not used very much in terms of tooling. So you can buy a really, really cheap 3D printer for 500 quid, and you can actually 3D print the dies. That was really what we would want to explore with this research, that you can have a very, very, you can use these new technologies to create a tool-making process that is very cheap, so you can experiment with the process. So, and it kind of worked. So these are all 3D printed dies. It's surprising that they kind of withstand the high pressure of the extrusion, but it really works. It's just some of the early tests. And then we moved on. You can do kind of really complex shapes because, with the 3D printing, the geometries, where this would, if you are manufacturing a thing like this with lots of cores, and you have to do that in terms of conventional engineering, it's really complex, really costly. In terms of 3D printing, it's really, it's very, very affordable, and you can really experiment. So complex things like this can be done through 3D printing with lots of cores in terms of the extrusion. The project over extrusion was structured with lots of little kind of case studies, and the idea with the extrusion research was that we would learn from the different case studies. So we were working with industry application with traditional fired ceramics, but we're also working with high-tech material. So we're working with something called ceramic matrix composites, which is used in jet engines. So it's a ceramic fiber with a ceramic slurry, but it never been extruded. So we got some of the material from Rolls-Royce, and we then kind of experimented with ways of extruding with this material, which has fiber in it, and that's where we actually get to the kind of the cob or the earth break element. So we were using, and I think that's a critical thing, we were using some of the knowledge that we gained from these kind of investigations into one kind of ways of extruding with fiber into clay break. So moving on to cob, which is actually what, which is kind of the I presume the core interest of this audience. So a part of this in research was to see what we could do in terms of extrusion with cob or earth breaks. And we didn't really know very much. We had an idea we wanted to do it, but we really didn't know very much about cob. So we went on a course and went through the kind of process and realized how labor intensive it is. And I mean, it's incredibly low impact, but it is very labor intensive. And critically, it also doesn't comply to building regs. So you can't build a cob house that conforms to the U value that a new build would require. Then a project which I'm sure a lot of you will know, the Cobage project from University of Plymouth, their aim was to do exactly that, to develop a way of building with earth or cob that does comply with building regs. So you can build with it, so it actually meets the standards. And the way they've done it is through this double layer, a structural layer and a thermal layer. So you get the U value from the wall, but also the structural capabilities with the structural layer. But again, it is still a slow process. You're obviously working with a frame here. So the idea is, can you use extrusion with these materials to create a quicker process where you can make bricks or cob units through extrusions? That was really our goal. So cob extrusion. So here our extruder here, so obviously the COP material, which I'm sure many of you are familiar with, with the fiber and the soil, the sand, and we started really using precisely the recipes of Plymouth to see whether we can do it. So a structural mix and a thermal mix, exactly like they specified. We started with the thermal mix and extrude that. But it really didn't want to extrude. It was far too fibrous. It just absolutely just locked in extruder, just come back. So through iterative processes, how much clay did we have to add to actually make the composite extrude? We ended up with this composition down here. So 6 to 8, so still more hemp sheaf in terms of the fiber, and then the clay. And we just about get it to extrude like that. The surface quality wasn't great, but then we started using some of the knowledge that we gained from the other investigation, particularly into the high-tech ceramic matrix composite. And with that investigation, we adjusted the nozzle length. So you see here, these are the nozzle lengths in terms of the extrusion dies. And the longer you have the nozzle, the better you can get the resolution. So I have got a... So this is the extrusion. So you can get actually really, the longer you have the nozzle, the better surface resolution you get. So actually really very crisp. The structural layer extruded absolutely fine. It was only the thermal layer that we had, or the thermal mix that we had some troubles with, but the structural layer absolutely fine. So then we were kind of onto the two mixes. And then really to highlight that we used 3D printing a lot for the tool making, and then the possibilities that gives in terms of different geometries. So with 3D printing, you draw a shape in a drawing package on a computer, and you can kind of there's lots of different packages available, also some open source, so you don't have to pay for. Relatively easy skill to learn, and then you 3D print. And 3D printers are becoming incredibly affordable and accessible. So these are some of the machines we have in the research lab. The one on the right, probably some of the cheapest models you can buy, under 200 pounds, but incredibly powerful in terms of what it can produce. So we would use a number of different machines. Some of the machines with a finer resolution for the nozzle, and some other machines for more coarse resolution for what's called the pressure plate. So they kind of lead in before it hits the little film of what 3D printing looks like. So this is the time lapse. It's not as quick as this, but it is fairly quick. So a nozzle or a pressure plate will be printed in maybe 3 to 4 hours, and you have a number of printers. Then you can kind of iterate the tool making process very quickly. So yeah, this is what it looks like. Very much speeded up. Finish. Again, this is the kind of 3D printing industry is constantly evolving. This kind of latest Chinese, really high quality but very affordable. 800 pounds for something that can print amazingly high quality. Yeah, so you can do variations really quickly. That was really the base of the research, was to set up this system and to explore how quickly can you change shapes, how quickly can you explore the different shapes. So once you printed the shape, you can put it on the extruder and you can create a shape for the profile. We were cutting the shapes, obviously with the fiber. You can't use a cutting wire, which you normally do with the clay brick. The kind of representing saw here with a particular blade worked really well, and then you can start playing with the shapes, and that's really the vision with the research, that you can create this workflow where you can explore these different interlocking shapes. So what can work? One of the ideas was you one of the ideas is that you can interlock. You can rather than use frames when you are building with corp, you can use the kind of an interlocking design, so you can quickly get the structure up. So you can build wet just like you would normally do with corp. Exploring different ways that you can orientate the shapes. We still to kind of test what that would do in terms of having the fibers in a particular orientation in terms of weathering, cornering, and also taking some. We thought they were really beautiful, so we took some sort of kind of sexy corp images in the studio. But this way of kind of using possibilities of creating different profiles and different voids within the wall really to be explored. These are just kind of proposals from our side, but we really want to kind of put this out as a proposition for other people to explore further as a system. Another thing to kind of point out is that with the extrusion you can create voids within the extruded brick. This is a die. I have it outside, so you can have a look, where you have what's called cores. So you can create. You can't. It's a bit dark here, but the extrusion here has has these kind of voids inside. So you can create voids inside the bricks, and this can be of significance if you want to have. Well, it was our kind of proposal in terms of increasing the thermal performance of the bricks. We did have some, it's not completely without its problem, the 3D printed dies, because they are still plastic. So we did have some issues in terms of breakage, but you can then reprint and you can strengthen certain areas. You can print with different materials. It is also worth highlighting that the material we use typically for the 3D printing with is what's called PLA. It's a bioplastic based on cornstarch. And we've been doing some tests with Ibstock, the big brick manufacturer. How well does it actually perform in a really full-on industrial situation? So this is what they normally use for an extrusion die, a stainless steel insert. As you see there on the left, these are some of the versions that we've been printing on the 3D printer. And this is one of them that has been through 10,000 bricks there on the right. So it's amazing that this kind of bit of cornstarch can withstand the pressures in terms of industrial production. So really moving from this kind of research into industrial applications really seem to be possible. Another kind of element of looking at the materials used for tooling, that we've been experimenting with a flax-based filament, 3D printing filament, which is entirely compostable. So once you finish with the die, you can home compost the tool and it'll completely disappear. But it is still worth recycling. It is still a highly manufactured product. So we recycle the waste and then we turn it into we have a filament maker, so we can recycle what we don't use. So in terms of testing, so once we've set up this system and the proof of concept is there. We've done some tests in terms of the output of the extruded corp bricks. It seemed to be an area that is still quite novel in terms of producing earth bricks or corp bricks. So there's very little literature on it that we could find. We've done a series of structural tests on the various extruded samples. And interestingly, we've actually found that that pure clay is actually very, very strong in terms of compression test. But the fibers, it's interesting that the fibers still add something, and the way that the fibers are orientated in terms of this compression state does make a difference. So the kind of horizontal layering of the fiber provides the best compression performance. Also, flexural tests, as you'd expect, pure clay doesn't perform very well in terms of kind of this flexural four-bended pressure test, where when you add the fibers, it really does help the performance. One area which we still, which is problematic in terms of extrusion is that when you extrude, you align the fiber, you also align the clay particles, and for some reason you do get a lot of shrinkage width-wise. Length-wise, there's very little shrinkage, but width-wise there is up to 10%, which is quite significant. So we really are looking to what can we do to bring that shrinkage rate, because that could be problematic in terms of future use, particularly if you're building wet with the units. We've done some thermal conductivity tests. We really hope we can get close to Plymouth's performance in terms of the thermal mix, but we're nowhere near that yet. It does help to have the voids in there, which we can pack with more insulating material, but we're still not there in terms of performance. But really, to kind of sum up, this is research, and it's kind of knowledge that we want to share, and we really want to kind of put it out there as a possibility for other people to use this system and to play with the geometries and to see how this kind of innovation can be relevant in terms of earth brick production the kind of tool-making workflows where you utilize 3D printing and new technology. How can that be utilized in terms of experimentation and new ways of making earth brick? I think that is the end. Thank you.